Hello everyone, and welcome to my channel. In this project, I aim to present examples of creating a counter using a push button and external interrupt capability on an Arduino Nano board. The push button is pulled up, so pressing the button sets the digital value of pin to 0, whereas in its normal state, it holds a digital value of 1. Let me to provide you with an explanation of the external interrupt capability before proceeding with this project. External interrupts are a fundamental feature of microcontrollers that allow the processor to respond immediately to external events or signals. When an external event occurs, such as a change in voltage level on a specific pin, the microcontroller can interrupt its current operation to handle the event, execute a specific interrupt service routine (ISR), and then return to its previous task. Here are some reasons why external interrupts are essential and advantageous in microcontroller applications. Real-time responsiveness. External interrupts enable microcontrollers to respond promptly to external events without the need for continuous polling. This real-time responsiveness is crucial in applications where immediate action is required based on external stimuli, such as sensor inputs or user interactions. Power efficiency. Instead of continuously monitoring input signals, which can consume significant processor resources and power, external interrupts allow the microcontroller to remain in a low-power state until an event occurs. This helps conserve energy, making it suitable for battery-powered or energy-efficient applications. Simplified code structure. Using interrupts can simplify the overall code structure by allowing the main program loop to focus on core tasks while handling external events separately through interrupt service routines. This modular approach enhances code readability, maintainability, and scalability. Precise timing. External interrupts provide precise timing capabilities, allowing microcontrollers to respond with minimal latency to time-critical events. This feature is particularly valuable in applications where precise timing is essential, such as in industrial control systems, communication protocols, and motor control. Multitasking and multithreading. By utilizing interrupts, microcontrollers can efficiently multitask and handle multiple concurrent activities. Each interrupt source can trigger a specific ISR, enabling the microcontroller to manage various tasks simultaneously without the need for complex scheduling algorithms. Event-driven programming. External interrupts promote event-driven programming paradigms, where the execution flow is determined by external events rather than being strictly sequential. This programming model aligns well with many real-world applications, simplifying development and improving system responsiveness. Overall, external interrupts play a vital role in enhancing the performance, responsiveness, and efficiency of microcontroller-based systems, making them indispensable in a wide range of embedded applications. Two types of software and hardware models can be utilized for using external interrupts. Here's more information on hardware-driven external interrupts in Arduino Nano. Interrupt pins. Arduino Nano has several pins that can be used for external interrupts. These pins are mapped to specific interrupt lines of the microcontroller. For example, on the 8MEGA328P microcontroller used in Arduino Nano, digital pins 2 and 3 are associated with interrupt lines INT0 and INT1, respectively. Hardware interrupts on Arduino Nano can be configured to trigger on different types of events, such as rising edge, falling edge, or level changes. This flexibility allows you to configure the interrupts to respond to specific signal conditions. Interrupt service routine (ISR). When an external event triggers the interrupt, the microcontroller pauses the execution of the main program and jumps to the ISR associated with the interrupt. This ISR is a special function that handles the interrupt event. It should be kept as short and efficient as possible to minimize interrupt latency. Interrupt priority. On Arduino Nano, external interrupts have predefined priorities based on the interrupt number. For example, INT0, associated with digital pin 2, has higher priority than INT1, associated with digital pin 3. This priority scheme determines the order in which interrupts are serviced and multiple interrupts occur simultaneously. Interrupt disabled during ISR. By default, interrupts are automatically disabled during the execution of an ISR to prevent nested interrupts from interfering with each other. This behavior ensures the integrity of the ISR execution but also means that other interrupts may be missed while the ISR is running. In summary, hardware-driven external interrupts in Arduino Nano provide a convenient way to respond quickly to external events with minimal latency. They are commonly used for tasks such as detecting button presses, reading sensor inputs, or interfacing with external devices in real-time applications. Pin change interrupts, SINs, are a type of interrupt available in many AVR-based microcontrollers, including the 8MEGA328P used in Arduino Nano. While pin change interrupts are not strictly software-driven interrupts, they can be considered a hybrid between hardware and software-driven approaches. Here's how pin change interrupts work and why they can be considered somewhat software-driven. Triggering mechanism. Pin change interrupts are triggered by changes in the logic levels of selected pins rather than by dedicated hardware signals or events. When a pin changes state, from high to low or low to high, and is enabled for pin change interrupt, it can trigger an interrupt request. Hardware aspects. Pin change interrupts utilize the microcontroller's hardware to detect pin state changes. However, they do not have dedicated hardware interrupt lines like external interrupts, INT0, INT1, etc. Instead, a single pin change interrupt vector is used to handle interrupt requests from multiple pins that are enabled for pin change interrupts. Polling in ISR. When a pin change interrupt is triggered, the microcontroller jumps to the ISR associated with the pin change interrupt vector. Inside the ISR, you typically need to determine which pins cause the interrupt and take appropriate action based on the current state of those pins. This may involve reading the state of the pins and performing conditional checks to identify the pins that triggered the interrupt. So, while pin change interrupts do rely on hardware mechanisms to detect pin state changes, their configuration and handling involve software-defined parameters and logic. Therefore, they can be considered somewhat software-driven, especially in the sense that the programmer must configure them explicitly in software and implement the logic for handling pin state changes inside the ISR. The performance differences between pin change interrupts, SINs, and external interrupts, INT pins, on AVR-based microcontrollers like the 8MEGA328P, used in Arduino Nano, depend on various factors, including latency, interrupt handling overhead, and ease of use. Let's compare these aspects. Latency. External interrupts, INT pins typically have lower latency because they are triggered by dedicated hardware circuits when specific events occur, e.g., edge transitions on the pin. This results in faster response times to external events. Pin change interrupts, SINs may have slightly higher latency compared to external interrupts because they rely on software polling to detect pin state changes. The delay introduced by the software polling can result in a slightly longer response time compared to hardware-driven interrupts. Interrupt handling overhead. External interrupts, INT pins have lower interrupt handling overhead because they are directly connected to dedicated interrupt vectors in the microcontroller. As a result, the microcontroller can quickly respond to external events without much additional processing overhead. Pin change interrupts, SINs may have slightly higher interrupt handling overhead because they typically involve more complex ISR logic to identify which pins triggered the interrupt. Inside the ISR, the software must determine the specific pins that caused the state change and handle them accordingly, which can introduce additional processing overhead compared to hardware-driven interrupts. Ease of use. External interrupts, INT pins are often easier to use and configure because they are tied to specific pins with dedicated hardware support. In Arduino programming, you can set up external interrupts using the attach interrupt function with a straightforward syntax. Pin change interrupts, SINs can be more complex to configure and use because they are not tied to specific pins but rather to port groups. Configuring pin change interrupts requires setting appropriate bits in control registers and implementing logic to handle multiple pins within the selected port group. While this approach offers flexibility, it may require more manual configuration and setup compared to external interrupts. In summary, external interrupts, INT pins, generally offer lower latency, lower interrupt handling overhead, and greater ease of use compared to pin change interrupts, SINTs. However, pin change interrupts provide flexibility in monitoring multiple pins within a port group and can be useful when the number of available external interrupt pins is limited. The choice between SINTs and INT pins depends on the specific requirements of the application and the trade-offs between performance, flexibility, and ease of use. My recommendation to you is to utilize microcontroller pins that have hardware interrupt capability as much as possible, especially when you require very precise timing for external interrupts. In this project, we are indeed using both hardware external interrupts and software external interrupts via pin change interrupts, SINTs, unit. In the examples I'll show you, we'll use built-in Arduino IDE functions. With each button press, it's intended that a variable of type integer increases by 1 unit, and its value is displayed in the serial monitor. Example 1. In this example, we'll connect the push button to pin D2 of the Arduino Nano. Additionally, we'll utilize built-in Arduino IDE functions. We intend to use the hardware external interrupt method in this example. Example 2. This example is similar to the previous one, with the difference that we want to utilize register-level programming to create hardware external interrupts. Example 3. In this example, the push button is connected to pin A0 of the Arduino. Additionally, we'll utilize built-in Arduino IDE functions. Since pin A0 of the Arduino board does not have hardware external interrupt capability, we'll use the pin change interrupt method. Example 4. This example is similar to example 3, with the difference that we'll use register-level programming to create a pin change interrupt.